Well, why don't I go ahead and get rolling? Hopefully others that may join later will be able to catch up either now or via the recording. So today anyway, it's our lab session, so what I'm going to do is go over what I assigned you as far as homework in the last go-round, and you should be able to see on the screen here the slide I had showed you before. So the task was to implement and run an R script that would run the Handson Example 1 that you had done before using the WinBUGS GUI. And I suggested that you use the linear1b .r script as your template. And let's see, what else did I say here? Go ahead and hard code the data set in the R script. Use 3 chains of 10,000 iterations each, with a burn-in of 5,000 iterations for each chain and thin by 5. Produce the diagnostic tools and summary tables via the parameter plot table function, just like we did in the linear1b example, and then plot the posterior predictions overlaid on the data. So most of this involves fairly straight ahead modifications in linear1b, but part of the problem is I'm real familiar with that script and you're not, so it might have been a little more puzzling to you, not having worked with it before. Let's see, somebody says they don't see my screen. Okay, let's see if I didn't punch anything on here. I probably forgot to push a button. Yes, I did. I'm sorry. Okay, hopefully my screen should be coming up for all of you now. And what I just said actually was just a reiteration of what you see on the slide here, assuming you're seeing it now. Okay. Sorry, I just forgot to push a button. Okay, so again, we're going to be using that linear1b as our template, so let's go ahead and go at it. So here I'm starting out with pretty much the same clean slate you probably would have seen in here. Let's go to our Handson 1 example. Okay, and you should have something, so you should have something like this mehandson1.odc file, and let's start with that. So let me close this for now. Let's fire up WinBUGS. There we go, and let's grab linear 1. not linear1b, I'm sorry. Let's grab this ME1 Handson 1 for the model we're going to work with. So this is the model that we're going to be working with. Now let's go ahead, and since we're going to use the linear1b script for our template, let's go ahead and grab that thing. So I'll just grab it. There we go. And let's copy that over to the ME2 Handson 1 directory in there. In fact, I'm going to go ahead and rename it using that model name, the ME2 Handson 1. Okay. And in fact, even before we go any further with the model here, let me go ahead and pull that up so we can see it. So I'll open up R. And then from R, let's open up the script. There we go. Okay, so that's our linear1b script here. So first of all, let's go ahead and deal with a little bit of the bookkeeping on here. So we're now going to be doing the nonlinear regression example that we had from Handson Example 1. The first step I'm doing I don't really need to do, but let's go ahead and rename this here. So we'll just call it a nonlinear regression example. And the name of the model then that we're going to use is MI2 Handson 1. For the example directory, in this case, it's going to have the same name, so I'll just say that it's the model name here. Okay, so a lot of this stuff is going to stay the same. So we needed to change those so that it would find the right information in the right places. We go down, I think all this stuff up here where it's assigning the paths to various places to variable names, that I think all stays the same. Let's see, down here that all stays the same. So where we start changing things is we're going to have to change the data that we're putting in, the initial estimates we're putting in, so that's going to change as part of this. So where are we going to get that? Well, let's go back to WinBUGS where we opened up our model code. Okay, so we have our model code in here. Well, actually, let's start with one thing. In order to use R to WinBUGS, which is what we're doing inside this R script, we need to save the model as a text file. And the preference here would be to use only have the model in it, not the data and so on. And recall that in the original example here, we not only have the model here, but we've got the data and the initial estimates all in the same file. So let's just go ahead and grab the model itself. So we go from the second time you see the word model here down to the closing braces here. We're going to copy that. And then let's come up with a new file here. So just say new. And let's copy what I just... Okay, there it is. Okay, and then we'll do a save to a text file. So let's go ahead and save it. So I'm going to do a save as. Okay, and where it says document ODC, let's change that to plain text. Right there. And we got to go head down to the directory we want it to be in. So we're going to head down to our MI2 Handson 1 directory. Okay, and let's name it MI2 Handson 1.txt. Actually, did I use a period or is that a comma? Let's see. Okay. So that's now saved as a text file. If everything went well, if we go back to our directory there, we should see, let's see, MI2 Handson 1.txt, right. And I just noticed I misspelled my R script. Fortunately, that's not a big disaster, but we may as well clean it up here. Let me just redo the save as here. Put a nice little D in there. Okay, so we've done that. Then we've created our text version, our plain text version of our model. Now the other thing, recall that in my specification for the problem I said let's just hard code the data right in the R script rather than reading it from a file for this example, mainly because that's the only thing you've seen how to do with the linear 1B example so far, and in our later examples I'll show you how to deal with reading it from a file. And of course many of you probably already know how to do that. But, okay, let's go ahead and just select that data set, copy it. And let's go back to our R script. And where we have our bugs data here, we're actually going to get rid of the old one that we used for the linear example, and we'll pop in the data that I just copied right here. And I see it doesn't seem to be wrapping here. Let's go ahead and throw in a few carriage returns. Okay, so that is now, let's see, oops, sorry for the overshooting my scrolling there. Let's see if we have the right number of parentheses at the end of it. So bugs data, we got a list, and yeah, I think we're all set there. So okay, and did I delete the other? I guess so. So we've created our data set by just copying it over. For our initial estimates, what I propose doing is using an approach similar to what's shown here, though I'm going to simplify it a little bit here and not try and do the nonlinear regression, least squares nonlinear regression here. We'll just hard code some numbers in here. Now let's go back to our bugs and see what is it that we actually need. Okay, so we need to put in initial estimates for emacs, for the log of EC50, for gamma, and for sigma in here. And as we do that, we're going to have to keep in mind there's going to be some constraints on those things, because recall that some of these are over restricted intervals. So emax has to be between 0 and 100. Log EC50, well, that can be anywhere, no problem there. Gamma has to be between 0 and 10, and sigma between 0 and 1,000. There's a few different ways we can do that trick, but I'll show you the one that one way here as we do this. So let's put in some initial estimates. Maybe as a template, I don't even remember whether these were good initial estimates or not, but we'll go ahead and use them as the center of the ones that we're going to generate. See, okay, so we're back in R. Let me just sort of copy that here so we can see it while we're working. Okay, so that's what I'm going to work with, is the middle of the thing. So let's start with emax. So emax is going to be, well, I want it to be between 0 and 100. You know, there's different ways we could sample that. I could use a scaled beta distribution, for example, is one way. But the way I'm going to do it is let's actually sample from a log normal distribution, but truncate it on the top. So we're going to truncate, so emax will come from a log normal distribution that's truncated at 100. So the way I'll do that is we're actually going to take the exponential of a normal distribution. And actually what I'm going to do here is I've got to say, I'm going to use a function. This is one of these so-called handy-dandy functions I've provided you. In fact, let me show it to you. Let's go to our bugs tools directory here. In there's something called beagle.sb.utilities. Somewhere in there you'll find something called ironarmtrunk. Oops, going too fast. I know you're in there. There it is. Okay. Right down here. So got rnorm.trunk. And notice that the arguments are similar to rnorm, but with a couple of new ones. So it's rnorm. It's got the number of random variables to generate, the mean, standard deviation of the normal distribution, and then a lower and upper bound on it in here, which you can see what the defaults are, just the standard ones for a normal distribution, but you can set them to finite values here. So that's what we're going to use, is this rnorm.trunk function. So where do we go? Let's go back to here. So call it rnormtrunk. We're only going to generate one every time this function gets called by BUGS. And let's see, for the mean, let's go ahead and use this, but notice this is taking exponential, so I actually want to put a log of 75 here. So it'll sample from that. Now, so the mean, if we ignore the truncation issue anyway, would be at 75 after we take the exponential. Let's see, what do we do for, for the standard deviation, I'll just make up something. I don't know, 0.2 is as good as anything, which would correspond to a 20% CV. If you want it more over dispersed than that, we could certainly make it bigger. Let's see, so we need emacs to be between 0 and 100. So let's see, the lower bound we don't have to worry about, because keep in mind the bounds are also, we're going to be taking logs, and log of 0 would be minus infinity, and that's what it is already. So we only need to set an upper bound, which is going to be the log of 100. Okay, and hopefully I got enough. Do I have enough parentheses in there? No, I need one more. Okay. So that's the trick I'll use to restrict my initial estimates, because if you give initial estimates that are outside the range of the prior distributions, you will get an error. Okay, what's next here? We have our log of EC50, log.EC50, and let's make that. Now that one can be, we can just go directly with a normal distribution on that one. Okay, again, I was going to do one of them. I guess I centered that at 4 on there. Let's go ahead with that. Again, let's make that one a little broader. Let's make it more 0.4 as our CV. That'll correspond to a CV for the EC50. Let's see if I got it all. Yeah, no truncation there, and then we've got our gamma, and I'll use the same trick for truncation on that one, as well as using a exponential or a log normal distribution. One sample centered at, okay, it's going to be log of 1, which is actually 0, but and again, let's make a reasonably large CV on that. And in this case, we're going to put an upper, what did I say, log 10? So it's going to be log 10. One more, yeah. Okay. And same game with the sigma. Let's see, where do we have that centered? 10. Okay, we'll go to 0.4 again. What did I say that was? An upper of 1,000, I think. Yes. And I think that's the works. So that would be our initial estimates. Okay, and then we got to tell it what we want to monitor and save here. We certainly want these things, so we want like emacs, EC50. Let's add in gamma and sigma. I think that's all the ones that we'd want to plot and such, and then we have to do with we want our predictions, which I think I built into the model. Let's take a look at that. So we use the name here. What did we call it? Oh, there it is. So I called the posterior predictions fxa.pred. Where am I going here? So we need to change the name here from ypred to fxa.pred. Okay. So we've actually done everything we need to on the sort of initial book work here. So we've dealt with our file paths, we've put in our data, we've put in our initial estimates, and we've said what we want to monitor in this. We don't need to change the rest of the stuff there. And then we have to specify things like how many chains, how long are the chains, and so on. And let's go back to the specifications here. So I recommended here that you try it with 3 chains with 10,000 iterations each, 5,000 burn-in iterations per chain, and thin by 5. So those translate pretty quickly over here. So we've got our 3 chains already. We want to make the number of iterations now 10,000 and change the number of burn-ins to 5,000 per chain, and we're going to thin by 5. So that's all there is to that. There shouldn't be anything you need to change. Oops. Shouldn't be anything you need to change in the bug statement here, other than, as I mentioned, when you're first working with something, when you first try something, sometimes it's worth going ahead and changing clear WD to false and debug to true, so that you can actually get into the WinBUGS GUI as it's when it runs and potentially fails, so it doesn't close out and you can't see the error. So that might be worth it. In fact, why don't I illustrate that here right now? So let's go ahead and change this to true and clear WD to false. We'll go ahead and oops. Okay, we'll do that. Okay, the next bit again is kind of boilerplate. We don't really need to change anything there. The part where I said, let's see, what did I say? I said produce diagnostic plots and summary table via the parameter plot table statement. Well, that's what's going on basically here. There's a couple of things where, first of all, on top we're opening up our PDF graphics device, so that'll open up PDF files. This is selecting out the parameters that I want to plot in here, and then here I run parameter plot table to get which does some diagnostic plots like history plots and density plots, but it also produces a summary table which gets written out in the following statement right here. So that takes care of that, and those have been written pretty generically, so all we had to do is change the model name up top and it should work okay. And the part that you need to spend a little time changing would be the plotting routine to do the posterior predictive distributions. For this particular example, the changes aren't too great. Most of it is changing a few names around because the structure of the data isn't all that different from the linear model case. So in particular, for when what this statement's supposed to do is just grab the columns in the posterior matrix that contain the posterior predictions for our factor 10A inhibition. And recall that had a different name. It wasn't called YPRED, it was called FXA pred in there. So that's one thing that would be different. And all this is saying is basically find all the columns that have names that are FXA pred and plus an opening square bracket in them. And I guess when I run this, I'll show you actually what those names look like so you can see how it corresponds to that. Let's see, the next thing I do here is I just build a data frame that contains our data. Recall that the original data frame is in the form, or I'm sorry, the data is currently in the form of a list in here. And there's a couple of ways I could actually write this. I could actually just do an as data frame and get most of it, but I'll just do it the same way pretty much I did here. But let's use names consistent with what we did in the new model. So if you recall in our model here, the names we used were FXA for our factor 10A percent inhibition, and where'd it go here, in COBS for our independent variable here, our average plasma concentrations. So let's be consistent with those names. So let's call, instead of calling that X, that's going to now be COBS, and we'll do this, and it has to be that way here because that's the name we used in the bugs data list. And then FXA corresponds to our y-axis here. Change that. What else might we need to, oh, that shows up again here where you see the y. I have to change that to FXA. Let's see, and I guess it shows up again in the plot statement. So here it's y versus x. So where it says y here, I've got to make that FXA, and where it is x, it's COBS. In here, and I think everything could stay the same, but why don't we use names for our axes that are a little more appropriate for what we're doing here. So x is going to be our, what was it, our time averaged ME2 plasma concentration, and then, and I don't remember what units we used or if I even specified, and then our y label here is going to be our time averaged factor 10A inhibition in percent. Okay. I think that's pretty much all I need there. Now, in theory, if I did these correctly, I think I've actually made all the changes that I need to make this run. Let me take a breath here, and before I actually try to run this, since I kind of ran through this pretty quickly, see if there's any questions. Okay, nothing's popping up here yet, but if you're typing, continue there. I'll keep my eyes open to see if something pops up on the screen here. So again, the main things here is in fact, for all the examples we'll be doing through the course, the sort of core template will stay pretty much the same. And in fact, for most production work I use things that are fairly similar to what you're looking at here. The main things that tend to change is is getting a little more fancy down here, where I start looking at diagnostics and other kinds of posterior predictive checking and various simulations and so on based upon the model. So the big changes tend to happen down in this last section for most production work. Okay, let's go ahead and see what happens when we actually run it. I guess first of all, let's save it before we lose it. Okay. And let's go ahead, let's go ahead and select the whole mess and run it. Okay, so far so good here. Most things are in red, which they should be. You can see it's sort of going through the bits. It's about to fire up the, whoops, I see I had an error someplace. Okay, now I've got lots of black. Okay, let's go see where I made a mistake. Okay. Probably misspelled some silly thing or whatever. Okay, that suggests I made an error probably somewhere in this bit of, probably made an error in my initial estimates function here. I probably made some, actually, what does it say? Non-numeric argument. Okay, well, what did I do? Probably typed some letters where I intended to be numbers or some silly thing. Okay. Ah, right there. That was probably the fatal flaw there. Okay, let's find out. Let's actually do a quick thing here, sort of compile that, and let's actually run it and see what happens. So BUGSINIT. Okay, it looks happy now. I suspect it wouldn't have before. That's one that by the way was an illustration of a quick test to see if your initial estimates function is working. As you just go ahead, and what you saw me do is I went ahead and selected it. I clicked on, there's this one here that for run line or selection, which there's a button there, or you can get to it, you can also get to it from the menu here under the edit menu. So I ran that, which all it does is define it at that point, and then down here I actually call it to see if it produces numbers. And it produces numbers. I can't guarantee they're logical numbers, but they're numbers. Okay, so we broke it. Let's go ahead and try again. See if I made any other errors here. Here, let me clear this in case we need to go hunting for problems we did. Okay. Okay. If at first you don't succeed. Okay, it fired it up. It looks like it's behaving. Oops, sorry, I actually wanted to leave that open so you could see it. Okay, so when you run this, it actually opens up the screen. In fact, if you want to interact with it, you can. So for instance, I can come down here and hit the update button. And when I do, you can actually see it increment the updater here. If I wanted to do a trace on the variables as it's going, I could do that, for example. I think this will probably finish before I can get there, but yep, it finished already. So it's writing the stuff out. It does a few diagnostics in there. Now, because I had specified debug equals true, it actually won't close. I can actually still see the GUI stays open. I can interact with it. I can see any of the things like the plots that are done by default in here. Actually, let me close these windows so you can see them. So you can actually see those plots here even before you look at the ones that R is going to produce. Now here, in fact, you're getting a lot more than you possibly want. What am I doing here? Okay, because it produces a summary table, but because of the font size I'm using here, you can't actually see the columns very well. But we're going to get actually a better summary table anyway, so frankly I usually ignore the contents of the log except possibly for error messages, which we don't have in this case. So since everything ran fine, let's go ahead and just close this, and when I do, it will return control back to R, and you'll see the script will take off where it left off. I may have to go back and see if, I see. It was complaining the directory already exists, and that's because it created the directory when it did the first failed run. So I think that was the only error that we had up here. Let me double check. Yeah, so if you have that situation where you've run it already, it's no big deal. It's just, yeah, okay, it created the directory in the previous run, so the fact it already exists is a benign error in this case. Okay, so it ran. Did it make any sense when we did? Let's find out. Let's go over here. So one of the things that you see, also because I said don't clear the working directory, you'll see some extraneous files here. You see some initial estimates files and a script file and coda files and stuff, which we won't actually need in this instance, but they're there. Let's actually go to the other operating system here because it's a little easier to there we go, to look at some of these for me on that. Okay, let me open up our directory. So this now, the directory, this ME Handson 1 directory inside this outer ME Handson 1 contains the results of what we just did. Let's see if they look any good. So let me open up the plots that we did. So the first few plots here are the ones that are created by parameter plot table in there. So we see here our history plots. Sigma looks pretty clean. That's a nice fuzzy caterpillar. And of course you've actually seen essentially these before when you did the Handson Example 1 via the GUI. This should be about the same as that. And you can see with Gamma, Emacs, and EC50, they've at least all come together and seem to be bouncing around roughly the same distribution, but there's still a lot of autocorrelation apparent in these within this frame, so they aren't quite fuzzy caterpillars. They're kind of, they're not real nasty wiggly snakes, but there's a bit of that going on. So if you wanted to make inferences about those three parameters, you might want to run this for maybe something like 50,000 iterations instead of 10,000 in this case to get better precision. But they're not bad. But it isn't what I'd want to use for a production report in this case. Okay, let's see what we get next. Here you get our marginal posterior distributions for the various parameters. So you see, you got gamma that's centered roughly around 1, sigma roughly around 6. We got what EC50 is kicking around. Oh, what is that? It's kicking around 120 or thereabouts, 110. And Emacs is getting up towards the 100% mark. Looks like it's centered roughly around 85 to 90% in here. And with uncertainties taking it pretty much from 70 up to 100%. Similarly on the EC50, the uncertainty is fairly broad here, taking us from roughly roughly 60 to about 150 in here. Let's see, this is our, again, we'll talk more about the Gelman-Rubin-Brooks plots with the next lecture. But you can see in here what you're looking for is you want these things to be sort of asymptotically approaching 1 and being less than around 1.05, at least out here at the tail end. I think that's pretty much true for all of these. The only one that's not entirely clear because the scale's a bit bigger is maybe the EC50 and the Emacs. Those are somewhat bigger scales, but I think even those have made that. Let me get rid of that. Okay. So let's see here. Anything else I wanted to, let me show you that. And so finally, this is the plot. Well, that's not quite the plot we wanted. Now what I had used is I used the template code from Linear 1B, and if I had thought about it, I would have realized what happened here. The original Linear 1B data, the data on the x-axis was already ordered. It was already in increasing order, but our data isn't. So I had to do one more step before we did the plot. And let me go ahead and do that. If we come down here, I needed to, after we put all of this mess together, need to do something like x1 is our data frame that we want. In fact, let me show you, maybe the top of that. Okay, so if I say head x1, so you can see the data in here. So we've got our concentrations, our factor 10A inhibition, and a designator saying whether it's observed the 5th, 50th, or 95th percentile here. But notice that the concentrations are not ordered in any way because, of course, they're just kind of the way they came from the different individuals, from the different patients. So in order to make a prettier plot here, we'd like to order those. So we can do that right here. I'll just say x1, and then inside here just say order. It'd probably be sufficient just to order them by x1 $COBS. If you want to make the resulting data set a little prettier, you probably also want to order it by type. But yeah, it's actually not too critical in this case whether you do or not. So since we're not using it for anything else, I think that'll be sufficient. And what you'll end up with here, in fact, I'll just run it here without putting it into a PDF, just put it on the screen. Okay, yeah, you can see it right there. So now we've got an appropriate picture here. So you can see all of our data points here. And then you've got the blue here represents our posterior median. And then the red dash curves then correspond, if we look at that in the vertical direction here, those correspond then to point-wise 90% credible intervals for our predictions. So you can think of that then as that's saying that, okay, if I was to recruit another patient and and give the same treatment here, you would be, and let's say I gave a treatment and their concentration was a particular value, let's say 200 for their time average concentration. Then I would come up here and I'd say, okay, well, there's a 90% chance that new patient's average factor 10A inhibition would be between those bounds. So let's see, we went ahead and saved that. I guess if I really want to make this pretty, I should go back and scrolling too fast again. Let's back down. Let me actually go ahead and rerun from where we open the graphics device down to the bottom. I'll go ahead and rerun that just for completeness. Okay, and assuming I did that right, that should, now let me go back up again here. Okay, let's see if it cleaned it up appropriately. Yeah, that's what we wanted to see. Okay, so it did create the correct graph in the PDF then. So that's actually basically all there is to the homework assignment on this. I suppose if we thought about it, we could probably come up with all kinds of other things we can do with it, but that's probably far enough on that. That's actually pretty much all I was planning on covering. I guess I'll open it up again to see if there's any questions about what we've done here, or if you have any, maybe there are things you thought of that you would want to do with the analysis. If you have any questions about how to approach that. Something popped up. Let's see here. Okay, it says please explain more about how initial estimates were created in the R script. Well, let me see if I can help there. It depends a bit on sort of what the exact intent. So recall that the BUGS function, with the BUGS function, one of the ways that you can specify the initial estimates that will get passed to WinBUGS is to where for the init's argument here to pass a function which will generate a list of initial estimates. And what we did back here then is create those. Now I'm not sure if you were going after that or if you were going after where did the 75, 4, and 1 and 10 come from, because those were, the one comment there I guess I can say is they were fairly crude sort of numbers. In fact, for instance, if we go back and look at the plot, we can probably get some guesses here. So for example, if I look at this, I'd say, okay, of course I've got a curve through it, which is leading our eye a bit much, but even without that, I can kind of look and say, okay, it's definitely curving off, so something like an emacs model might work. It looks like it might end up asymptoting to something between 70 and 100. Exactly where in there I don't know. If I eyeballed it, I'd say between 70 and 90 or so would have been my guess. So that's kind of where the emacs initial estimate came from. And then if I start thinking about, okay, well, if I think it's going to go up to say around 75, 80, then I go down here to somewhere around half of that, go across and say, okay, that's where I'm going to put my initial estimate for my EC50 in this. And I don't know what is e to the fourth. I forget where that came from. But anyway, if I was eyeballing it here right now, I'd probably say, okay, looks like it's probably less than 100, but not a lot less, 80, 90, something like that on that scale. Looking at the curvature on this, I don't think the gamma would be a lot different than 1 in this. I don't see a lot of sigmoid character in this, so that would be my first ballpark guess. So that's kind of where, some of this in terms of the standard deviation, I could probably even sort of eyeball that a little bit. You can kind of see how big the spread is on this thing and say, okay, well, the spread on this is maybe over around 20. So I'll take about half of that as my best estimate for a standard deviation. Again, that's real crude, but that's where we can come from. Now let me go back to the mechanics. So here I create again, what I can give to BUGS is something that will return a list that has the form of initial estimates. And what this does is it does return a list. I've used random number generators so that when I do multiple chains, every time this function gets called, I'll get different values. In fact, I can illustrate that here. If I type in BUGS init right here and hit that, you'll see I get a set of values. Now, actually, let's make this full screen here. Now, if I type it again, I'll get 4 more values, but they're different values. So every time that it gets called, I will get a different set of values here. So, and the same thing is true. So when I do 3 chains, Bugs is going to call Bugs init 3 times, and every time it's going to get a different set of values for initial estimates. As a result, the 3 chains are going to have different starting points in here, which is exactly what I want to serve as convergence diagnostics. On the other hand, I try to center them somewhere near what I think my best guess is. What else to tell you about it here? Well, the other thing now, by the way, when a little bit about the mechanics in here. When the R to WinBUGS function runs, that bugs function that comes from R to WinBUGS, it actually creates a bunch of files in here. So, and in particular, if we look here, you'll see, well, like here's inits2. If let's just open that up with Notepad here. Notice what it looks like. It's a list that with the emacs, log EC50, gamma, and sigma. So that's the initial estimates for the second chain. And in fact, the way this whole thing will run is Bugs is creating initial estimates file for every chain. It creates a data file, which actually it moved over to I think into our subdirectory here. So yeah, it creates a data file that you can see here. And it creates a script. So I think that's still up here. Yeah. And it creates a script. So this script was actually created by the bugs function in here. So it creates all the functions it needs to run WinBUGS using a script. And then it runs a DOS command that launches WinBUGS with the script as an argument. So that's all it's doing, is it's creating all these files and then launching a script. It just automates that process for you. And then once it's run, it goes out and grabs the results and pulls them back into R. So I guess anyway, I guess the question here is, did I answer your question? And maybe a little more, I hope. Okay, apparently. Any others out there? Let's see. Oh, yeah, the question was, could I please post the R script? Sure. In fact, why don't I go ahead and post the, what I'll do is probably zip up the sort of the result here and post that, which will contain the R script and the model and so on. Okay, well, if there's nothing else, I guess I'll sign off now. I'm going to try and make an effort to get at least next week's lecture recorded tomorrow, though it probably won't actually get, my guess is it probably won't even get posted until either the weekend or maybe our Monday or so. I'm crunching on a few things here, so hopefully I'll do it. If for some reason I can't, I'll let you know, and what we'd end up doing is taking advantage of the extra week that we have included in our schedule here as sort of and have our makeup week, but I'd rather not use that up if I don't have to. So I guess I will say goodbye, and I won't see you next week. I guess I don't see you anyway, but hopefully you'll hear from me by one mechanism or another, and then catch you live again in the following week. Okay, thank you, and see you then.